Hi all, welcome to this video. In the previous video, we were discussing about the introduction to integrated circuits, and our module itself is on integrated circuits. So we have seen the introduction and some preliminary things like the advantages of using ICs, etc. In this video, we are going to discuss further into integrated circuits, and we will be dealing with stages in IC fabrication. So how do these ICs get fabricated? So those stages are being discussed in this video. So come, let us start it. The stages for IC fabrication starts with material preparation. So in this stage, what we do is we will be deciding upon what material to work with, whether it is silicon or whether it is germanium or whether it is gallium arsenide, what kind of semiconductor we are going to use, the base semiconductor, the intrinsic semiconductor that we are going to use. And deciding that, we will be checking for the particular resources. For example, silicon, if it is silicon, then we will be looking for silicon dioxide, which is the most abundant thing to obtain from earth. So we will be taking silicon dioxide, we will be taking out purifying silicon out of silicon dioxide, and we will get it into a electronic grade material. And this electronic grade material will be further purified and its crystal structures will be made proper in a particular processing, and that is done in the second stage. In order to have better quality for ICs, or if you want to have defect free structures for ICs, then you need to have a perfectly aligned crystal structure for these electronic devices. So we need to grow the crystal of a silicon in a particular fashion so that there is much less defects in the crystal structure of silicon, and that kind of a crystal is grown. And when the crystal is grown, that is cut into disc shaped things called wafers, and it is on wafers that we are going to make all the circuits, and that is done in the second stage. And the third stage is wafer fabrication. So we have wafer and we have done preparing the wafer. Now what is left for us to do is the actual fabrication of the end product. So if we have the blueprint of whatever device we are going to fabricate, we will be fabricating millions of such device onto a single wafer. So a single wafer hosts a lot of similar structures, similar circuits on a single wafer. So suppose if we are going to fabricate a Core i7 processor, then a single wafer will be having lots of Core i7 processors being simultaneously fabricated onto the wafer surface. And after fabricating the wafer, we need to test whether each of the individual processors are working, okay, or the structures or the circuits are working. So that is done using testing, and after testing whether it is okay, then we will be cutting it out into smaller singular pieces, and each one of those pieces are called dies, and these dies will be bonded into and packaged into a particular IC package, and this is done in the fourth stage. So let us see the first stage. Let us learn more about the first stage. Our material preparation stage starts with obtaining silicon dioxide, which is obtained as sand, and we know that silicon dioxide is very much abundant in our sand. We will be gathering a lot of silicon dioxide sand, and we will make it react with gases formed due to the burning of carbon like coal, coke, etc., or wood, etc. So the silicon dioxide is made to react with the gas that is formed as a result of burning these fuels, and that gas will be having 98% of silicon, and that silicon containing gas is stored and it is further purified in a silicon reactor, and after purification we get electronic grade polycrystalline silicon as the end product. So this is the material preparation stage. Now we go to the crystal growing stage. In the crystal growing stage, the process is called Czochralski process, Czochralski, and there is another process called the flat zone process. We will be focusing on Czochralski process. Here what we do is, this is the setup for Czochralski process. It has got a chamber where you have inert gas filled inside, and you have RF heating all around a crucible, and here it is a crucible which can hold molten polycrystalline silicon. So whatever polycrystalline silicon that we have purified in the silicon reactor, we take it out and fill the crucible with those polycrystalline silicon, and we will increase the temperature, and it will be like melting point of silicon is around 1685 Kelvin. So we'll be keeping the temperature like that, and the furnace temperature is 1690. So it is just above 5 Kelvin above the melting point of silicon. So it is controlled by computer, and the thing is the crucible is slowly rotated in clockwise direction. There is another facility called seed puller. So this device on top of this is holding a perfectly pure crystal that we need to grow. So that pure crystal will be, or the seed, that is called the seed crystal, that will be held by this seed puller. And what it does is that it firstly it dips the seed into the molten silicon, molten polycrystalline silicon, and it will gently rotate in the counterclockwise direction. This one is in clockwise direction and this one is in counterclockwise direction. So while it is rotating, it will be slowly pulling upwards. So when it gets detached from the surface of the silicon, molten silicon, it gets solidified. And how it gets solidified is that it will align its crystal structure in such a way it aligns with the in accordance with the seed crystal structure. So the seed crystal will act as a template on which the rest of the silicon can grow. So the silicon grows by aligning it with the already existing seed crystal structure, and you get a perfectly aligned crystal by growing in this way. So as long as the pulling speed is computer controlled and the direction or the rotations etc are computer controlled, you get a perfectly oriented crystal as like this, and that crystal is called ingot. So here you can see the stages in this. This is melting of polycrystalline silicon, and after melting a seed crystal is introduced on top of this, and the seed is gently pulled upwards. So here you can see, as when you are pulling it upwards, a small solidification happens at the interface between the seed crystal and the molten liquid, and there what happens is it aligns with the alignment, the crystal structure of the seed crystal, and you can gently pull it upwards and upwards, and this happens at a very slow fashion, very slow fashion, and it pulls a big crystal out of it like this. So this is crystal pulling, and after having everything done, then it will be looking like this, a cylindrical shaped structure, and it is called ingot. And factors affecting the diameter are temperature and pulling speed, how much fast it is pulled. So if it is very fast pulling, then the diameter will be lesser, and if the temperature is properly not controlled, then it's not going to happen. So the diameter of ingot is around 200 to 300 millimeters, and the length is around 1000 millimeters. So this is how pure silicon is made out of polycrystalline silicon. So here it is, you cannot use polycrystalline silicon for polycrystalline means it contains crystal planes not aligned to each other. So in such if you are using polycrystalline silicon for making devices, then the efficiency of these devices will be much low, because the electron transport property in one region of that crystal will not be the same in another region because of the misalignment between the crystal structures. So we need to consider that problem in this. So that is why we are trying all these conversion process like Sokralski process and all to grow a perfectly oriented crystal. So this is the story behind Sokralski process. Now this is one a series of ingots made. So this is how it looks. You can see the portion where the seed has been connected. So here is a pure ingot made into shape. The next we will be doing a wafer preparation. So we have a ingot here, and we will be cutting the both ends of ingot so that you get a cylindrical shaped structure. And in the cylindrical shaped structure, we will be longitudinally marking a particular region and cutting it off or removing a longitudinal region like this. And this region is called a primary flat. It is basically used for aligning purposes and all. So all these processes are automated processes. So there will be pick and place arrangement systems in the procedure, and it requires some kind of alignment. So mechanical aligners will be depending on the position of primary flat to identify the alignment. And in addition to the primary flat, there will be secondary flat also. So secondary flats are similarly removed regions with respect to the primary flat. So its position will be with respect to the primary flat. Maybe it can coincide together. So there will be only primary flat only. So when you see, there will only be a primary flat. There will not be a secondary flat. That means that it is aligned together. So the use of secondary flat is that it can be used to denote what kind of doping is done in this ingot, whether it is p-type doping or whether it is n-type doping or whether it is having any other crystal structure. So it gives a measure of what kind of doping and what kind of crystal structure it has. Okay, so the crystal plane. So here you can see that this one is a primary flat region. This is the secondary flat, and the primary flat here and the secondary flat at a 90-degree with respect to the primary flat indicates that it is a p-type material with 100 crystal plane. And if the primary flat and secondary flat are diametrically opposite points, then it means that it is an n-type material with 100 crystal plane alignment. And if suppose your primary and secondary flats are at 0 degrees with each other, that means that there is only primary flat, then it is a p-type material with crystal plane 111. And if suppose it is at 45 degree with respect to the primary flat, then it is an n-type 111 crystal structure. Okay, so this is the way to identify what kind of doping has been done into the ingot. So this doping is happening during the crystal growing system itself. So here itself you can either make it a intrinsically n-type or intrinsically p-type material, and you can do other things in the later stages. So you can have a substrate where it is slightly doped, whether it is n-type or whether it is p-type, it can be slightly doped. Usually it is done like that. So after having the primary flats and secondary flats cut into the ingot, we will be slicing it with diamond cutters like this, and the wafer's thickness is around 0.4 to 1 millimeter. So this is how you will be cutting your ingot, and you cut it using a diamond saw, and what you get is a wafer, and the wafer is where you are going to make your circuits. And the wafers, both sides will be polished like a mirror, and you get it ready for the further processing. Let us stop this discussion here, and we will see the further details in the next class. Thank you all.